Well, good evening, students. It's Mr. Rich. It is another Sunday night Q&A. So thanks for stopping by. We've got a few students that are here, and I did have some questions that came in, and I am going to start with doing some AP Pre-Calc. If I don't get any questions that are sent in, I will be pulling up some AP Calculus and AP Pre-Calc that I've already got set up to work through some problems. I know a lot of AP Pre-Calc students this week that I've been tutoring have a test in Unit 1 on 1.7 to 1.11, so I'll probably work some of those questions. In fact, the problems that I think Corey sent in are from 1.7 to 1.11, so that's going to be where we start. If you are watching live, you can send questions to me. I take any math questions, from math to algebra to stats to pre-calc or even ACT or SAT. Some of you may be getting ready for the next SAT on October 4th. And if you've got a few problems that you want me to work, you can post those in the comments section. If you are one of my students, you have my email address and you can send it to me and I will pull it up and work it for you. Okay, so let's go ahead and get started. All right, let's bring up my screen. All right, thank you. And here are the problems that we had that came in from Corey. So let's pull these back again. Let's see where we've got. There we go. So these come from pre-calc, and this has to do with rational functions. So here is the first question that we're asked. It says that there's a rational function r given by r of x equals x minus 5 over x plus 7. What are all intervals on which that function is greater than 0? So what we're going to do here, there's two ways that I want to show you how you could do this. Probably your teacher has shown you the best way to do this is to make yourself an x-axis. And on this x-axis, we're going to plot any of the zeros that we have, any of the vertical asymptotes, any of the holes or x-intercepts. Vertical asymptotes, holes, x-intercepts. So we know that we have a vertical asymptote at x equals -7. So we are going to plot the value -7 right there. And we know that that's going to be, and I'm going to make a dashed line here just to remind myself that that's the location of the vertical asymptote. In the numerator, we do have a -5, x minus 5, which means we have an x crossing at 5. And there's no other features really for us to plot except the vertical asymptote and the 0. There's no holes anywhere, so we'll just leave those up there. Those are the two that we're going to plot. What we're going to do is we're going to pick what I would call test points or test values for x. I'm going to choose just to the left of -7. I'll choose x equals -8 to represent all the numbers that are to the left of -7. I'll choose x equals 0. That'd be the most convenient x value that is between -7 and 5. And then we will choose x equals 6. Then what we're going to do is we're going to go ahead and plug in these test values into the function. And I don't care what the number is. I just want to know whether it's going to give me a positive or negative to indicate whether the function is below the x-axis if it's negative or above the x-axis. So if you stick a -8 into the function, you will get a negative on the top and you'll get a negative number on the bottom, right? It would be a -13 over a -1. But the point is, a negative divided by a negative is a positive. So we are going to be above the x-axis there. When x is equal to 0, I'm going to have a negative on the top divided by a positive on the bottom. That's going to give me a negative value. So we are going to be below. And x equals 6 over here, that's going to give me a positive on the top and also a positive on the bottom. So it's going to be positive. So when is this function going to be above the x-axis? Well, it's going to be for all the values to the left of -7. So it's going to be from -infinity over to -7. I can't include -7 because it's a vertical asymptote. So I have to use a parentheses right there. And then it's going to turn positive again once I get past 5. So I would union that with 5 to infinity. And you can see that's exactly our answer here, answer C, like that. All right, so that's the method that you should use. Plot on your x-axis all zeros, which are going to be where the numerator is 0, x values that make the top 0. Any vertical asymptotes, anything that will make the denominator 0. And if you have any holes, I would plot those as well. So let's go down to number 12. So thanks, Corey, for sending that one in. This is another one that Corey sent in here. And this is also a rational function, and it wants to know when is the function k of x going to be less than or equal to 0, meaning when will it be at or below the x-axis. Well, when you take a look at the function itself, we know that there's a vertical asymptote at x equals 3 right here because of the fact that there is a x minus 3 factor in the denominator that does not get divided out by an x minus 3 on the top. So that means vertical asymptote at 3. There are no holes. So we don't have any holes there because I don't have any denominator factors that are going to get canceled by a factor in the numerator. But we do have some zeros, a place where the function will touch the x-axis. It's going to touch the x-axis at x equals 1 because of the x minus 1 factor right there. And it is going to be also at x equals -2. So that gives me 3 values that I'm going to plot along the x-axis. So we'll plot them, of course, in order, right? So -2 moving left to right, and then I've got an x equals 1 and an x equals 3. At x equals 3 is where we have a vertical asymptote. So I'm going to remind myself that that's the location of the vertical asymptote by putting a dashed line. These are zeros, so the function will be touching the x-axis right there. That gives me 4 different regions, right? So I'm going to select a test value for x to the left of -2. I will use a value here of -3. In between here, let's use an x equals 0. And then here we'll use x equals 2. That's between 1 and 3. And then we'll use x equals 4 right here. Then our job is to come back up to the original function, k of x, and determine when we stick in this test point, for instance, -3, am I going to get a positive or negative for the output for the k of x? So what I'll do is I'm just going to go factor by factor. I know I have a positive 3, so I don't need to worry about that. But when x is -3, when I plug that in there, it will give me a -4. But since it's raised to the second power, I know that that factor, x minus 1 squared, will always be positive no matter what value of x you put in because it has a power of 2. So I'm not even worried about that. So I'm really only going to, because these two are always positive. So I'm really just going to be considering those two. So when x is -3, I'm going to get a negative on the top divided by a negative on the bottom, right? -3 minus 3 would be a negative. So that means that's going to be a positive. That means that my function k of x will be above the x-axis whenever I'm to the left of -2. When I stick in the 0, that'll give me, for that x plus 2 factor, that will give me a positive. And in the bottom, it will be a negative. So therefore, a positive divided by a negative is a negative number. So that means it's now below the x-axis. When I plug in x equals 2, I get a positive on the top. I still get a negative on the bottom because 2 minus 3 will still be negative. That means it stays negative, which, by the way, is not really a surprise because it looks like the function was going to be bouncing off of that 0 because of that multiplicity of 2. So it looks like it is bouncing off of 1 and staying negative. And then we'll get to the other side of the vertical asymptote at 3, and then you plug x equals 4 for your test point, you get a positive on the top, a positive on the bottom, which means we are going to be above the x-axis. Now, this is asking, when is k of x going to be less than or equal to 0? Negative. Well, it's going to be starting at -2 and going all the way over to 3, but not including 3 because of the fact that it is a vertical asymptote. So there's our answer, D, right there. All right. That is it. Any questions? Post a comment in the comment section and let me know if you have any questions about that. And Corey, thanks for sending those in. Let me check to see if we got any more problems that came in through email. Checking it out here. I don't see any that have come through, but not to worry. All right, so before we jump over and do some problems in AP Calculus, followed by some problems in AP Pre-Calc, let me remind you of a few things. So I do SAT and ACT prep, and there is a test coming up on October 4th, as I mentioned at the beginning. There is another one in November, which is going to be, I believe, November 8th. So I am doing a group that is going to be starting October 2nd. So just a little bit more than a week away, I'll be starting one of my groups. We go for 6 straight weeks leading up to the exam. So if you are interested in that, you can see my contact information there that you could email me if you'd like to be part of that group. So just wanted to remind you of that. I also do a weekly AP Pre-Calc group that's right after this session at 9 o'clock on Sunday nights. And what we do in that group is we take questions on AP Pre-Calc, and I'll work problems. I'll give a lesson for the AP Pre-Calc students. They can send me some homework questions that they want me to work for that week. And, most of the students that I work with are on the same pace through AP Pre-Calc. And so we are kind of staying together as we move through that. So if you are interested in joining that group, let me know. It's a pretty small group, and we've got less than 10 students in it right now. Well, let me jump over and do a little bit of AP Calculus. If you are taking AP Calculus right now, you are learning the rules of derivatives. And so I wanted to work a few problems, and I wanted to show you some AP Calc derivatives. So let's do this, Chrissy. Take me back to full screen for myself, and I'm going to go grab one other worksheet that I think that we need here. So let me go grab that. So I want to start with the rules of derivatives for the what we call the power rule. So let me pull up some power rule questions for AP Calc. So we want to start with kind of the simpler things here. And let's pull this guy up. We'll bring this over. There we go. And then we're going to get into the product and quotient rule. So I definitely want to try working some of those. All right, that didn't come back. So hold on a second, Chrissy. I'm going to go grab that again. Didn't seem like I grabbed it. There we go. And there we go. 2.5 is what we want. Coming back. I think we got it. Okay. All right, Chrissy. So take me back to my screen. And I want to do some basic derivatives here. So I just want to start with what we call the power rule. Here's a function y. It's a function of t. And what we want to do is we want to take the derivative of this function. So the power rule to find a derivative is this. I'm going to give you the rule, and then we'll apply it to a few problems. And here's what it is. If you have a function, and I'm going to write it generically as a times x raised to the n power. We're just going to let a represent some constant, some number, and n also is going to be an integer. It doesn't have to be an integer. It could be any kind of an exponent. So it's also a constant. If you want to take the derivative of that, what you do is you multiply that exponent times the constant that's in front. So it would become n times a, and then you reduce that exponent by 1. So it becomes n times a times x raised to the n minus 1. And that's what we call the power rule. And it works for any time that you've got your variable and you have a numeric exponent here. And so I'm going to show you some examples of it, right? And most of you probably have already learned this rule, but if I'm going to apply that rule to this, what I would do to find the derivative, and y prime is what I'm going to call the derivative here, I take the 2 times the negative 5, which gives me a negative 10, and then we reduce that exponent by 1, and it becomes negative 10t to the first power. Then I move to the next term, and that's 4 times t to the first. So using the power rule, I'm going to take 1 times 4, which is 4, and then I would reduce that exponent down to a 0. All right, now t to the 0 is just 1. Anything to the 0 power is 1, so we really don't even write that. So this is what we would call a linear term. So when you take the derivative of a linear term, the answer is going to be just the coefficient, the 4 that's in front. And anytime we take the derivative of a constant, it's 0. So the derivative of this function that we started with is negative 10t plus 4. That is its derivative. Now, what is a derivative function? Well, hopefully by this point you've learned in your AP Calc class that this is really what we call a slope function. This derivative will give me the slopes of the tangent lines for this function at any place on its domain. I need to find the slope of the tangent line. All right, so that is how we use the power rule. Let's work a few more of those. Now, I'm going to show you this one here, number 12. So it's cosine of x minus 3 over x to the third. Now, I'm going to tell you what the derivative of cosine is here in just a second, but I do need to rewrite this term because I want that term, or I should say that that x to the third, I want that up in the numerator. So I'm going to rewrite this as cosine of x minus 3 times x to the negative 3. So I can use the negative exponent rule to move the x to the third up into the numerator by changing the sign on the exponent. Now, why did I do that? Well, because I want to take the derivative using the power rule, because I want to take this exponent and multiply it by the coefficient in front and then reduce the exponent by 1. That's the power rule. I can't use the power rule when that x to the third is down in the denominator. So anyways, I've rewritten that so that I can now take the derivative of this function. So the derivative f prime of x, I have to take the derivative of cosine. Now the derivative of cosine is negative sine of x. And then the derivative of negative 3x to the negative 3 would be a positive 9, right? Because I would be taking the negative 3 exponent times the coefficient negative 3, which makes it into a positive 9. And then I would reduce that exponent from a negative 3 down to a negative 4. And so this becomes the derivative of f of x. Let's go down here because I want to show you one of the other things that you'll be doing quite a bit in this class. And that is finding equations of tangent lines. So let's take a look at number 34. The instructions here are to find the equation of the tangent line to the graph of x, to the graph at x equals a for whatever value they give us. So here's our f of x, 6x minus 16 times the square root of x. And they wanted me to find the equation of the tangent line on this graph over at x equals 4. So here's what we have to do. We're going to find the derivative of this function. But before I take the derivative, I'm going to change this second term into x to the 1/2 power. I'm going to change that radical into its fractional exponent, x to the 1/2. Now what I'm going to do is take the derivative, f prime of x. Well, the derivative of 6x, remember that's 6x to the 1, so it's going to be 1 times 6 or 6 times x to the 0 or just the number 6. Here I take the 1/2 times negative 16, which gives me a negative 8, and then I have to reduce that exponent by 1. And 1/2 minus 1 would be 1/2 minus 2 over 2, which would be a negative 1/2. So this is going to be x to the negative 1/2. Now what I'm going to do is I'm going to get the slope of the tangent line at x equals 4. So I'm going to find f prime of 4. So that's going to be 6 minus 8 times 4 to the negative 1/2. Now, how do I evaluate that? I'm not going to use a calculator here. I'm going to do 6 minus 8 over 4 to the positive 1/2. Because I'll take that 4 to the negative 1/2, move it down into the denominator, change its exponent from negative to positive, and you should know that 4 to the 1/2 is the square root of 4, right? It's 2. So that's going to be 6 minus 8 over 2. 8 over 2 is 4, so it looks like that value is going to be 2. So what that means is that when we look at this function and we look at its graph and we go over to where x is 4 on its graph, the tangent line slope is going to be 2. But now I need to know the point of tangency. I need to find out what the y value is on this function when x is 4. So I'm going to find f of 4. Okay, I needed f prime of 4 to get the slope of the tangent line. I need f of 4 to get the point of tangency. I need to know the y coordinate where we're talking about on this function. So I'm just going to type in here 6 times 4, plug the 4 in for x, minus 16 times the square root of 4. Well, that's 24 minus 16 times 2. That would be negative 32. 24 minus 32 is negative 8. All right, so what does this tell me? This tells me that on this function, we have the point of tangency. I'm going to abbreviate that POT. The point of tangency is 4, comma, negative 8. The slope of the tangent line, I'll abbreviate that SOT. Slope we got as f prime of 4, it's equal to 2. That's all that I need to make the equation of the tangent line, because I'm going to use what we call the point slope form for an equation. It's y minus y1 is equal to m times x minus x1. So anytime that you're told to come up with an equation of a line, we're going to be using the point slope form for a linear function, because the x1, y1 is any point that's on the line. The m is obviously the slope. So what I'm going to do is I'm going to put negative 8 in for y1, 4 for x1, and 2 for m. So this becomes y plus 8 is equal to 2 times x minus 4. And that is the equation of the tangent line. Now, as you're learning calculus, what you want to do is you want to check answers using Desmos and see if this even makes any sense. Graph the function. So I'm going to come over here to Desmos, and I'm going to make a graph of the function itself. F of x is equal to 6x minus 16 times the square root of x. So there is the function right there. Okay, interesting function. I maybe would not have guessed it would behave like that, but there you go. That's what it is. Now I'm going to do let's plot the point of tangency first of all. Let's just plot the point that we knew that we are talking about, right? We said that when x is 4, we got a y value of -8. Let's just confirm that that's actually on this function. 4, -8. And there you go. So I just plotted the point here. So you can see, indeed, 4, -8 is right there. Now, when I plot the tangent line that I came up with, let's move this out of the way here. I'm going to plot that point. It should be, I'm going to see if I can sketch on this. No, I can't sketch on this. But what it should be is it should be a line that's coming right along here and then nicking and just barely touching the curve at that one point and then keep going. Let's see if that's really what happens. Y plus 8 is equal to 2 times x minus 4. And indeed, you can see that that black line, which is the equation of the line that we came up with, it is the tangent line. It does hit that curve at one point, 4, -8, and keeps going. If you zoom in, or let's zoom out, you can see that that does look like what we call a tangent line, hitting the curve at only one point. If we zoom in and we keep zooming in, what will happen is you won't even be able to differentiate between the tangent line and the curve itself. They kind of blend together, and that's how you know that you did find the tangent line. So I've zoomed in an awful lot. You can see the scale here is 8, 8.02, 8.04. So we are really super zoomed in, and you can't even tell the line. If I turn the black line off, you will see the green curve, and then turn it back on. So you can see they're superimposed on top of each other. It's not till you zoom out that then you can see that they are separate functions. There you go. But that shows you how you find equations of tangent lines. You're using as your template what we called back in Algebra 1, the point slope form. I always tell my students, when you were studying Algebra 1, Algebra 2, your teacher told you that y equals mx plus b was like, we kind of generally considered that to be the best form of a linear function. Yeah, it is good to have a linear function in that form because it automatically tells you the slope and it tells you where it's going to cross the y-axis there at whatever that b value happens to be. However, when it comes to creating equations, this is not the one that we want to use. To create a linear function, you want to use the point slope form because you don't have to have the y-intercept to create it. You can use any of the points that are on the line, x1, y1. Just know one point on the line, the slope of the line, and you've got your equation. All right, I want to, before we leave calculus and go do a little bit more on pre-calc, I'm going to go over to look at what we call the product rule and the quotient rule of derivatives. So let me define the product rule for you. If you have a function that you're trying to find its derivative, and it's actually two functions of x multiplied together, it would be nice if the derivative were f prime, the derivative of f times the derivative of g, but it's just not true. That is not how you take the derivative when you have a function of x times another function of x. Instead, you have to do it this way. You have to take the derivative of the first function times the second function plus the first times derivative of the second. That's what we know as the product rule. How do we use that? Or what does it look like? Or how do we know we're supposed to use it? And then how do we use it? Let me show you some examples. When you take a look at this function here in number 1, it's the function 8x times sine x. And our job is to find the derivative of that, or what we would call the slope function for it, the derivative. Well, the derivative is not found, as I said, by saying it's going to be the derivative of the 8x times the derivative of the sine. It's not that way. Instead, what I'm going to do is I'm going to define the 8x to be the first function that's being multiplied, and sine x is the second one. So I will take the derivative. Remember, this is going to be my rule that I'm using. If I'm trying to find f prime of x, I'm going to take the derivative of the first times the second plus the first times derivative of the second. So the derivative of 8x is 8, and the second function is just sine x. Then there's a plus sign as a part of the formula. Then I'm going to put the first function, 8x, multiplied by the derivative of the second function. And the derivative of sine is the cosine function. And so this becomes here, students, the derivative of that function using the product rule. Now, I'm going to show you an example of using the product rule when you have to find the equation of a tangent line. So let's go down here and we shall do that. All right. So what we'll do is we're going to find the equation of the tangent line of this function at x equals pi over 3. Now, I have to tell you, right, you are supposed to know when you get into AP Calc, you're supposed to remember your unit circle that you had memorized from AP Pre-Calc. If you don't have that memorized, be sure to know it. You got to go back and at least memorize that first quadrant, right? Pi over 3 is first quadrant angle, so we'll be okay as long as you know what's going on in the first quadrant. So what we're going to do is we are going to come up with an equation of a tangent line. So we are going to use y minus y1 equals m times x minus x1. Now there's the x value, pi over 3. So that's going to be my x1. Let's go ahead and find y1, which would be the y value of this function when x is pi over 3. So let's go ahead and do that. This doesn't require calculus. I'm just plugging in pi over 3 into my function. That becomes 8 sine of pi over 3 times cosine of pi over 3. Well, in the unit circle at pi over 3, sine is going to be root 3 over 2. So we're going to write that as 8 times root 3 over 2. And cosine of pi over 3 is 1/2. So hopefully you remember those. Let's go ahead and do that multiplication. Well, that is going to be 8 times root 3 times 1, which we'll call 8 root 3. And then 2 times 2 in the bottom will give me 4. Let's go ahead and simplify that, and we'll call it 8 divided by 4 is 2. We'll call it 2 root 3. So the point of tangency, where the tangent line is going to hit the curve, is going to be at x equals pi over 3 and y 2 root 3. It's going to look like that. Now we have to get the slope of the tangent line. So that's where the derivative comes in. So I need to find f prime of x. So we're going to have to use the product rule because it's 8 sine x times cosine of x. So I'm going to take the derivative of the first, right? This 8 sine x is the first. The cosine x is the second function that's being multiplied. So we'll take the derivative of the first, which is going to be 8 cosine of x, times the second, which is cosine of x, plus. Then the product rule says to take the first function, 8 sine x, times the derivative of the second function. And the derivative of cosine is negative sine x. So that is the derivative function using the product rule. Well, what we want to do is plug in pi over 3 because I need to know the slope on this curve, on this f of x, over at x equals pi over 3. So we have to now find f prime of pi over 3. It'll be 8 times cosine pi over 3 times cosine pi over 3. We'll move this minus to the front since it's sine x times a negative sine x. So that'll be negative 8 sine pi over 3 times sine pi over 3. All right, so that'll be 8 times 1/2 times 1/2 minus 8 root 3 over 2 times root 3 over 2. Well, let's go ahead and do our math here. This is going to be 8 times 1/2 is 4 times 1/2 is 2 minus 8. Well, root 3 times root 3 is 3, and 2 times 2 is 4. So it looks like it's going to be 2 minus 8 times 3/4, which would be 2 minus 6, which would be a -4, like that. All right, so what do we do next? I've got everything I need. I had the point of tangency up here that I'm going to plug in for my, this one right here will be my x1, and this will be my y1 that I'm going to plug in up here. I just found the derivative at pi over 3, which is -4. That's going to be the m. Right, so let's go ahead and come up with the equation by just plugging those values into the point slope form of the equation. So this should be our tangent line equation. Y minus 2 root 3 is equal to m -4 times x minus pi over 3. That's it. Now, it doesn't look pretty, but that's it. You can just simply leave it. That is a linear equation. And that would be the tangent line that should hit this curve at x equals pi over 3. Now, hopefully I did this right. As you saw, there's a lot of places I could have made a mistake, some sort of a math error or a calculus error for that matter. But let's see if this is legit. So we'll graph the function to start with. F of x is equal to 8 sine x cosine x. Now let's just make sure. They want me to put this in parentheses. Desmos doesn't like me to put those trig functions right next to each other. All right, so that's going to be 8 sine x cosine x. So the first thing I want to do is just see if the point of tangency is legit, if it really is on the curve. So we're going to do pi over 3 comma 2 square root 3. Okay, it looks like it. So you can see right there, it's not some point that's randomly out in space somewhere. It does look like it is on the curve. So at least we have success there. Now, when I put this equation in, it should make a line that would come down and just nick that curve right at that point and then keep going straight. Let's see if it works. So here is the equation. Y minus 2 times the square root of 3 is equal to -4 times x minus pi over 3. I think we got it. I'm going to bring this out so we can get a better look at it. And sure enough, you can tell that right there at that point is the tangent line. So we actually got the equation of the line that is going to hit the curve at x equals pi over 3 at that one point. And when you zoom out, sure enough, that's it. Okay, so finding equations of tangent lines is something we do a lot. And there's several applications to it that I won't go into here, but you'll be learning as you go through units 2 and 3 as to why we want to know equations of tangent lines. Okay, I think what we'll do now is make a transition over to pre-calc after we've done some calculus. I didn't get to the quotient rule. I'm going to make one comment about the quotient rule. You know, there's a lot of acronyms in math that we use, like SOHCAHTOA to remember the 3 trig functions and their ratios. Well, there is a saying that we use for this quotient rule that I'm surprised when I hear that teachers aren't telling the students what the saying is, because this is the one acronym that after all these years, I still use every single time I have to take the quotient rule derivative. I use this saying in my mind to make sure I get it right. Now, I'm going to show you the derivative when you are dividing two functions of x. Like you can see, maybe number one, it's the ratio of a x function on the top and an x function on the bottom, which we call rational. It's a rational function is what that's called. But how do we take the derivative? Well, the derivative is not the derivative of the top divided by the derivative of the bottom. It would be nice if life were that simple when it came to calculus. It'd be nice to say that it was just take the derivative of the top and put it over the derivative on the bottom. That's not what it is. This is what it is. It's g times f prime minus f g prime over g squared. And I may say, where do these things come from? Where do these come from? They all come from that limit definition of a derivative that you learned at the beginning of Unit 2. We taught you the definition of a limit. I think I went over where how we use that limit definition. But if you take a generic function that's a ratio and you put it into that limit definition, you can prove that this is going to be what you get every time you take a derivative of a ratio. Now, what's the saying? I'm not going to do any problems on this. I'm just going to tell you what the saying is, okay? It's this: low d high minus high d low, square the bottom, off we go. It's a rhyme, actually, right? Square the bottom, off we go. So what does that tell me? So it tells me low means the bottom. Low, the bottom function, g. D high means the derivative of the upper. Low, d high, minus high, top function. D low, derivative of the low. Square the bottom, off we go. That's it. All right. So anyways, that is how I memorize the formula with that saying. And every single time I use the quotient rule, I'm saying that to myself. Next week, maybe we'll do some quotient rule derivatives. All right, let's transition over to pre-calc. And we're going to do a little bit in 111. I want to first talk about slant asymptotes. How do you find equations of slant asymptotes? First of all, you have to be able to look at a rational function and know when would it have a slant asymptote. So when you look at this f of x, you can see that the top degree is 1 degree higher than the bottom. So this is a degree of 2, right? The exponent on the top, on the variable x, has a highest value of 2. Here it has a degree of 1 because it's x to the 1. So when the degree on the top is 1 higher than the degree on the bottom, you will have what we call a slanted asymptote. And if you want the equation of the line for that slant asymptote, you have to do polynomial division. So what we're going to do is we're going to take x minus 1 and divide it into x squared minus 6x plus 7. And we don't have to go very far on this. You don't have to do all of it to get the remainder. You just need to get the linear function that you're going to get here in these top two terms. So when you do this polynomial division, start off by dividing the two leftmost terms, which for us, it's x squared over x. And when you do that division, you get x to the first power. So you put that answer right here above the negative 6x. Then you're going to multiply the x that you have here, this answer that you put on the top. You're going to distribute that, multiply it through the x minus 1, and write the answer underneath. So x times x is x squared. X times negative 1 is a negative 1x. And then we are going to do subtraction. Well, x squared minus x squared is 0. Negative 6x minus a negative x would be the same as negative 6x plus x, right? Minus a negative turns it to a plus. So this ends up being negative 5x. We bring the next term down, 7, and we repeat the process. We're going to divide the negative 5x by the x. What is negative 5x over x? It's negative 5. That's as far as you need to go, because now I know what the equation of the line is. It's y equals x minus 5. That is the slant asymptote. Now, just like in calc, you want to get an answer and see if it makes sense. Is that really an asymptote for that function? So we can do this. We can say we've got f of x equals x squared minus 6x plus 7 on the top. And we've got to put this thing in parentheses here. Get rid of that parentheses in the beginning. That's going to mess it up. And then put that all over x minus 1. And then we will also do y equals x minus 5. Okay, so if we zoom out just a bit here and you take a look at that, you can see that that black line is the asymptote, and the function, as you go up to the right, it's getting closer and closer, just like an asymptote. That's what we expect asymptotes to be, the line that the function gets close to but never touches. And so we have the equation there of the slant asymptote. All right, so we have to know how to do that. Last thing here that I want to do is I want to go over 2 free response questions. This is the practice test that we went over, I think, a little bit last week. I worked some of these problems. What I want to do is go to the very end and show you what a couple of free response questions might look like for sections 1.7 to 1.11. And that's what we have right here. And just like any AP math class, there are usually going to be multiple parts to a free response. You can see that there really are 6 questions here in question number 1, and they usually go from easy to more challenging at the end. So they want those students who are struggling to have a chance to earn a few points there at the beginning to show that they know something about this problem. And then usually the last part is going to be the most challenging. Well, they give us the graph of a rational function. It's called R, the graph of R. And it does have a horizontal asymptote there, and it has a vertical asymptote. And it says, write the equation of the line that is the vertical asymptote for function R, and then write the equation of the line that's a horizontal asymptote. Well, when we say there's a vertical asymptote at 1, that line itself is x equals 1. Right? Vertical lines are x equals a number, where that number would be the x-intercept. So the answer here is just simply x equals 1. The horizontal line that passes through 1 would have an equation of y equals 1. Right? Easy enough there. So we got a couple of points there on letter A. Right, the next question says, determine the end behavior of function R as x increases without bound. Express your answer using the mathematical notation of a limit. All right, well, what does that mean? First of all, you have to know what this means, right? End behavior of a function is behavior of the function as it goes way out to the right or way out to the left. But they're talking about a specific end behavior, and that is the one where x increases without bound. That is a way of saying as x goes to infinity, increasing, getting bigger, out to the right is what that means. So that means that we have to write an answer that would say the limit of r of x as x approaches infinity, out to the right. And then when you look at the graph, and you say, gee, what happens when you go all the way out to the right? Well, it's getting closer and closer to the horizontal asymptote at y equals 1. So that limit is 1. So you have to know for this test that if someone shows you a function r of x whose limit as x goes to infinity is equal to 1, that's communicating to you that there is a horizontal asymptote at y equals 1. Because when x gets infinitely large, the y values are getting infinitely close to the number 1. So that's the answer to that one. Then the second part of B is to evaluate some limits. And they say here, what is the limit of the function as x approaches 1 from the right? And remember this, students, that if they're asking you to find a limit of a function, they're asking for y values out here. Your answers to this limit as x is approaching a number is going to be some y value. So what do they want me to do? They want me to go over to where I would be close to x equals 1, but on the right side of 1. So let's go up and take a look at where x is 1. Well, here's where x is 1. To the right of 1 would be on this section right here. If I were to approach 1, x equals 1 from the right, I would have to be traveling along this section right here. Because notice, as I'm climbing here, this thing's approaching the vertical asymptote. So to get closer and closer to 1 on the x-axis means I'm climbing and my y values are going up towards positive infinity. So the answer to this is infinity. The y values are going higher and higher the closer and closer I get to 1, x equals 1 on the right side of 1. If they had asked me, and they didn't in this problem, if they asked me what would be the limit as I approached 1 from the left, it would be over here because I would be going along this path if I were to get close to 1, but on the left side of 1. And that answer would then, I think pretty obviously, be a negative infinity right there. The next question is, what's the limit of the function as you approach 3 from the left? Well, find where 3 is. Let's get rid of all this. So here's 3. Here's where we're at 3. There's a hole there. But to the left of 3, if I were to get closer and closer, I would be traveling this path. And the closer that I get to 3 on the left side of 3, the closer I'm getting to a y value of 2. And so that is my answer. This answer right here is the number 2. The last part of number 1 on this free response is find all intervals for which the function is less than or equal to 0. Well, when is it less than or equal to 0? It's going to be only on this section right here. Less than 0 means the function is below the x-axis. So it starts at -1 and goes over to +1. So that would be from -1 to 1. Since it says or equal to 0, we will include -1, but I can't include 1 as the upper limit, the upper boundary, because it's the location of a vertical asymptote right here. Here's the vertical asymptote. So we never really get to that value of 1. So I do have to use a parentheses right there on the 1. All right, and then the last question here is write a possible equation in factored form for the function that we're looking at, right? And if you're taking a test this week on 1.7 to 1.11, I have to imagine that that's going to be one of the things your teacher is going to want you to be able to do, is look at this function and come up with what an equation would be or could be for that function. So let's do that. Well, I need there to be a vertical asymptote at x equals 1. So therefore, that has to correspond to a factor in the denominator of x minus 1. Since there's a hole at x equals 3, that means I need to have an x minus 3 on the top with a matching x minus 3 on the bottom, because that's how holes get generated when we're looking at the factored form of the numerator and denominator. You get a cancellation right there between those two. So I would have an x minus 3 and an x minus 3. And what else do we need? We also need to have a 0, an x crossing at -1. So that means I would put an x plus 1 on the top right there. So all three of those features, the x-intercept or the 0 at -1, the vertical asymptote at 1, and the whole at 3, they all correspond to parts of the function. And notice there would be a horizontal asymptote at y equals 1 because on the top here you would have a x squared, and on the bottom you would have an x squared. And when the exponents are the same, top and bottom, then your horizontal asymptote is at the ratio of their two coefficients. So it would be 1/1. Well, students, I think that is going to be it for tonight. If you are watching this and you're one of my students and you want me to work your homework problems, send them in to me before we start. Now, I did not look in the last half hour. I did not look to see if anybody sent me any other homework problems. I don't see any that are there. But you can send them way before. All you have to do is know the email address that I've given you, and you can send your practice or your homework problem to that email address, and I'll have it ready to go next Sunday night. All right, so you can definitely send that in to me. If you're watching this and you're not one of my students, you can wait till the session starts next Sunday at 8 o'clock, and you can post your questions into our comments here in YouTube. Well, everybody, I do wish you a great week ahead. If you're taking your AP Pre-Calc or AP Calc exams this week, good luck to you. Keep studying hard. Don't get discouraged, right? Anything at this point in math that's beyond Algebra 2, you've learned all the easy stuff. All the stuff that from here on out is generally not going to be all that easy. It's going to be, a lot of it's going to be new material. You just got to stick with it. It's anything else in life that you learn that's new. It's going to seem strange and weird until you work with it for a while. And then you'll look back at September. When you get to December, you'll look back and go, you know, that stuff back in September wasn't as hard as I thought it was. It'll start to make sense as you build your knowledge base in your classes. So keep working hard at it. It's going to pay off. All right, everybody, have a great week. I will see you next Sunday, 8 o'clock. Take care, everybody.